This video goes through the time and state-dependent resampling article in Python code. So as always, we start at the front page of the repository and then navigate to the examples. And if we look here, for example, number 11, the name of it is time and state-dependent resampling, and it's actually the accompanied code to an article with the same name that you can find on this SSRN link. So let's just go there and look what it contains. So basically this time and state-dependent resampling, it was initially introduced in the portfolio construction and risk management book. In this article we just give all the proofs of this new class of resampling methods that are left out in the book, where we just present the fully flexible resampling class. So this is some of the things that we write here in the abstract, and then we go to this introduction. So basically in the introduction we explain that it's crucial for us to be able to generate new paths for potentially very, very high dimensional markets and risk factors. And this is something that is described in the Portfolio Construction Risk Management book, where you can see that this is the input for modern sophisticated stress testing, views and optimization methods. So when it comes to this market simulation, there are of course many challenges. The good thing about resampling is that no matter how complex the cross-sectional dependencies are, we will be able to capture them, but they struggle to capture then the time series dependencies. So for example, if we take our raw data, we transform it into some station transformations, there will probably still be some time series dependencies that we need to capture. So if we just do a normal IID bootstrap, then obviously we will not be able to capture these time series dependencies. So that's why people have introduced different kind of resampling methods, which are usually these block bootstraps, and now we come with an alternative. Another method with resampling is also something called filtering, where basically you would estimate a model and then you will resample the residuals. So this is also something that you can find references for here in the introduction. The new method that we present here, the fully flexible resampling, it basically combines exponential time decay with arbitrary complex state conditioning, and we use entropy pooling to do that, which is described in great detail here in the second section. So all of this is something that I will allow you to read either in the article or ideally in the Portfolio Construction Risk Management book. It's just a clever application of entropy pooling, which was actually originally introduced in this article in 2013, but then the innovation that we make is to generalize it so that we can sample paths instead of just the same frequency as we have for data, because of course it might be the case that we have something like daily data, and then we want to be able to simulate weekly or yearly or however long we want paths of this data instead of just looking one day ahead. So this is what this method allows us to do compared to the original suggestion. So we write all the mathematics here and the resampling procedure, and the point here is that it will actually create an implicit Markov chain where we have these different state probability vectors. So this is something that we will show here in the case study. So before we get to the case study, there's this section that proves all the nice properties of this new fully flexible resampling method, and more generally the time and state-dependent resampling class. So basically this fully flexible resampling, it's just one instance of how you can do this time and state-dependent resampling. If you come up with some other ways of doing that, that's perfectly okay, as long as it satisfies some structure that we present here, then everything will work out fine. And this is what we show in the very extensive appendices, where we provide all the proofs that actually this procedure will generate strictly stationary simulations. So if you can take your market data and transform it into something that is stationary, or at least locally stationary, then you will be able to preserve these features when you use this time and state-dependent resampling class. So this is what you can read about here. So in the case study, We use the fully flexible resampling. This is the special case. And then we use an 1 month at the money forward implied volatility as the state variable, and we define some cutoffs with the 25th percentile and the 75th percentile. So again, this is something that you can read in the fully flexible resampling presentation. So basically here you can imagine that we use this 1 month at the money forward implied volatility, and this is something that we have from this time series simulation that follows with the Fortuna.tech Python package, and then we classify it into something which we call low volatility, mid volatility, and high volatility. Of course, in practice, for real world implied volatility data, we see more spikes, so probably you should separate it in a different way, but this is something that is up to you to perform the calibration. And then you can see that for each of these different states for the implied volatility, we can then compute some scenario probability vectors. So here you can imagine that this is the time index, and we have something like 20 years of daily data in this case. And then you can see that we introduce some exponential time decay, so as this usual exponential decay model, but then we also perform some state conditioning. So all these bar charts that you see, the green, the blue, and the orange, they all sum to 1 because they represent probability vectors for each of these different states with this exponential time decay. So basically this is how the resampling procedure is, that we start in some initial state and then we sample according to the probability vector of that state, and then we see which other state we end up in, and then we potentially update the probability vector and continue resampling like this. So the good thing is also that it allows us to perform some state stress testing, where basically we can condition on something like a sudden implied volatility spike. So even if we are in a scenario where things are quiet, we can use the method to introduce a high volatility state and then see the effect on our simulations. All right. So here, this is what we illustrate. Next is that when we do this resampling and which state we are in, here we condition on different states. First the slow volatility, mid volatility, and high volatility, and we can see that on the 1 month horizon, so this is the equity returns that we illustrate, it does indeed matter if we are in a high, mid, or low volatility state, because we can see that the distribution is wider for the high volatility state, it's very narrow for the low volatility state, and then something in between for the mid volatility state. But as soon as we look 1 year into the future, we can see that the state dependence starts to disappear, and this is of course exactly as we would expect it for a stationary simulation, and exactly how we want. So basically you can think about it in this way, that if we have a high VIX now, well, then it probably matters for how the future realized volatility will be in the market. So VIX is not a perfect predictor of that, but it has some predictive power. But if the VIX is high now, it doesn't really matter that much for the yearly, the 2-year return distributions. So this is basically what you see here, that the method has this property, and it's also there in the data. All right. So then here, we present the conclusion, which is basically a summary of all the things that I've presented, and then we provide the different references, and finally we have many appendices. So actually in this article, it's the appendices that are take up the most pages and actually contain the most new material. So here we provide very careful mathematical proofs of the properties of these new time and state dependent resampling methods. And of course this is quite important because you can imagine that this is an entirely new way of performing resampling of high dimensional investment time series. So of course we want to make sure that you can be comfortable using these methods, and that all the mathematics adds up, and that all the properties are as you want them to be. Okay, so I encourage you to go through, read this article, and then for the original introduction and to see how it all fits into a bigger picture, then read the Portfolio Construction Risk Management book. Now we'll go back to the code and then go through this just to see how the computations have been performed. So basically here there's also some reference to the Portfolio Construction and Risk Management book where you can understand the overall framework we use for simulation and where you can see actually the introduction of this fully flexible resampling method. Then we import the packages that we need. We load the time series data that follows with the FortiTech Python package, and then we perform some stationary transformations. So here for the equity series, it can just be the log return. For the zero coupon bonds, we compute constant maturity discount factors, and then we take log returns in these, because then it's basically log returns of a constant maturity zero coupon bond, which also has this nice stationary property. And then we look for the credit spread. It's the same. This is for the implied volatility. This is just the same transformations as for the equity index. We can get some nice stationary time series here. And then for the credit spread, we use the same transformations as we do for the zero coupon bonds. But of course, we are not able to have this nice interpretation in the credit spread case. But it doesn't really matter. What we want is just to have some data that looks stationary, and then after that, our simulation methods does not really care if we call it volatility, equity, or government bond or credit or anything like that. All right, so this is also something that you can read a lot more about in the Portfolio Construction Risk Management book. And then we collect these stationary transformations into one data frame, because this is what we want to work with. So here we first show you this 1 month at the money forward implied volatility, and then we perform this state classification that you saw before with the 25 and 75 percentile. And then we compute, just this initial prior exponential decay probability. So here I set the half-life at half of the period that we have. So basically that, you can look into this and see that you can actually compute this half-life and verify it, and then so the probability here will be half. Let's say halfway into our historical data, the probability here will be half of what it is on the latest observation. So this is how you can see this half-life parameter. And please verify that's actually also the case when you compute it. Okay, then we implement this fully flexible resampling, and here it's quite low level. We implement everything by hand. So of course there are many details that you probably would have a nice interface for, and this is what we have in the investment simulation module. But here you can see everything, the low-level computations, and then you can see how these posterior probability vectors have been computed. And now we just use them to simulate according to this procedure that is described in the article. So first we define a states vector, we define this resampling function, we have different initial states, we fix the seed just so that we can replicate these simulations, and then we allocate some space for computing these returns basically. And this is what we illustrate. We illustrate this 1 month simulation, and if you want to see the 1 year simulation, well, then you can adjust this horizon to 252. So that's what we assume. That's the number of trading days in a year, and then you can see that it converges to something that is quite similar. Here we show this state probability transition matrix. So basically, when you have these posterior probability vectors, then you can compute a transition matrix for the Markov chain. It's not something that is strictly necessary when you do resampling in this case, but it might give you some information about how sticky these different states are. So you can see that if we are in low volatility state, there's a very high probability that we stay in that state. There's a very, very low probability that we go to a high volatility state, at least in this simulated data. and then yeah, you have, if you are in this mid state, well, very high probability that you stay there, but then you can also go to a low and a high volatility state, and then yeah, for the high volatility states, the same thing. All right, so I hope that this video walkthrough gave you the intuition for how you can study this article, what this method is about. And then, as always, you should remember that if you give this repository a star, then people just tell me that the code runs faster. So this is what I encourage you to do for maximum performance.